Jeremiah Cunningham will be showing some of the programming interface. I'm going to say a little bit about the basic stuff first. And some of the things you see here are things he'll be showing in more detail, like this beautiful tree, so don't worry about that yet. So the calculator consists of a few sort of interlocked components. There's, well, obviously a keyboard. There's actually more than one, but this is the main one. There's a lot of functions that are set up in what we call guide pages, and I'll show some of that. There's also, as Stephen showed this morning, a predictive interface, which will start, we'll see more of that soon. And those of you who have seen it in Mathematica, it's a similar idea. From what I understand, it actually started with this project, made the leap to Mathematica, but is still going, this project is ongoing. Okay, so, and then the last of the major interlocking parts is the programming capability that Jeremiah will be showing in some detail. So, functions. Functions are divided. The stuff at the top is again Jeremiah's area, but at the very top. But below that, we have functions divided roughly into categories that correspond in some way to levels of school. This is intended as roughly middle school through, in America, so what we would call 6th, 7th, 8th grade through 14th grade. Halfway through college in the American university system or the equivalent elsewhere. So numbers is sort of a broad category, a coverall, but really as far as academic levels go, this starts with pre-algebra, algebra. The algebra and equation spans more than one level. It's sort of meant to be algebra and what we often call algebra 2 or pre-calculus. Then there's geometry, there's trig, which is another aspect, I guess, of pre-calculus. The calculus stuff itself covers more than just first year because, the standard first 2 years of college math typically go into at least 3 semesters of calculus, a bit of differential equations. So some of that's also in here. After this, we get into various individual sets of functionality that don't necessarily correspond to any grade level. So we have graphing, stats and probability, linear algebra, which is typically taken as one course, but which different people encounter at different levels in their school careers. Discrete math, then logic, financial math, and then we have a couple of areas beyond that maybe are a little bit more off the beaten trail. So we tried to arrange this to some extent at the front in terms of increasing level of course, and then in terms of what we were guessing might be popularity of usage for different areas. This is subject to change. Okay, so having explained that, now on this is the main guide page. And what we're seeing is just a handful of representative functions from each of these different areas. So, I don't know, let's go, geometry. So we get into a lot of the things that you might expect to find in a high school geometry class. Compute the distance between points, given a array, compute the angle to the positive x-axis, that sort of thing, and your standard circle stuff. Triangles, perimeter, of course, and that many people learn about that long before they get to high school geometry, but because it's all under the heading of geometry, we put it here. There is some redundancy. Some of these will also show up in the pre-algebra guide page, for example. In fact, I think perimeter of triangle might be one of them. Things that, huh? No. No, I want to get you excited about this, but if I show it to you, then yes, you can see one of them. I was building up to like a crescendo. We were going to do triangle from SAS, and you completely like ruined the moment. And I don't know. I just want to go cry. Okay. So triangle from SSS. Triangle from SSS. Hello. Okay, so the idea here is we know from geometry that a triangle is uniquely determined by 3 side lengths. So we're going to give 3 side lengths, and it's going to give us, if it's working right, some information back about this triangle. And I'm not going to be cheesy and do 3, 4, 5 because people know about that triangle. It's a right triangle. And I'm not going to do 3, 5, 4 either because that's the same thing in disguise. Okay, and I'm not going to do 3, 5, 9 because I know that that won't actually work. So does 3, 5, 7 work? I think it should. Okay, and compute. What? Okay, the last time I tried this, it wasn't so misbehaved. So what it's done, I know what it's done. It's giving us the information that I want it to give. It's repeating the lengths of the 3 sides, 3, 5, and 7, and then under them, well, each side has with it an opposite angle, and it's giving the angle measure. But that's not the way this was supposed to look. It's supposed to actually show you a picture, and okay. This is cyber dust. This is the effect of cyber dust. I should have, anyway. Okay, so back to here. Now, because I'm persistent and stubborn and all that, I'm going to try one more. So we'll give it an angle of, do we have a degree sign on this? Thank you. Okay, so we'll give it 25 degrees and another angle of 75 degrees. And the included side length will be 4. And I'll compute again, and we'll see what happens. Okay, this is a little more to my liking. So here's the sort of thing that I was hoping to see the last time, where we actually have this triangle and labeled, and if it worked correctly, you'll see the 3 angles, 2 of which I gave as input. The third is obviously, very easy to compute since the sum has to be 180. And then the corresponding lengths of the opposite sides, one of which I think I gave the one that was, I hope I gave the one that was 4. I don't think I typed in those other things. Okay, so this is an idea of the kinds of things that one gets. And this computation is a little bit uncommon in the sense that most things don't try to both show a picture and give more information, but some do. And in particular on the pre-algebra page, there's some neat sorts of things there that are both pictorial and otherwise. So let's see. I'm going to try to wrap up quickly so Jeremiah can jump in. And I have to do this before he gets the idea to hit me over the head with the microphone. So let's see. Computing with fractions. Add fractions. Hold on a second. So 2/5 plus, oh, thank you. Whoops. Now I missed it all. Push the input field.
Yeah.
Where, here?
Yep.
No.
That usually, there you go.
All functions. Okay, let's try that again. This time I'll get the 2 correctly. 2 over 5 plus 3 over 11. Whoops, did that wrong. I forget how much is already laid out for me. I shouldn't forget. I was the one who laid this stuff out. I'm not joking. Okay, and so we get this, because it's pre-algebra, we don't usually spell out all of the steps and that sort of thing, but because it's pre-algebra, it seems sensible to spell that out. I will add that once again, there's supposed to be some kind of picture that goes with it. I'm starting to get very suspicious about the picture code. But there was supposed to be a graphic that also, in effect, shows how one adds fractions graphically. Well, I won't get into that. It's something for me to look into later this week.
Will you get the same result if you just typed in 2/5 plus 3/11?
No. No, then it would just give you a straight result, the actual computation, but none of this other stuff. So that, one of the things about doing this through guide pages is we know where it's come from, we know what level we're aiming for, so we might give more or less extra information with the computation. Anyway, with all that, we have about enough time for Jeremiah, so.
All right. So the next thing that I'm going to talk about is actually my favorite feature of Wolfram Calculator, programming mode. I was always one as a kid to pick up graphing calculators and figure out that they could program. So I'm very happy to introduce this functionality in here. All right. So one of my favorite features of Wolfram Calculator is programming mode right here. And we give you this template here to start with. It's a typical Mathematica function template here. We have your function name, your variables, which you can just continue to add more variables as you see fit, as many as you need, though preferably keep them lower for clarity. We also have our code view body here, which I'll actually move this keyboard so you can see. We have our code view body here where you'll enter your Wolfram language code here. It's a multi-line code body. Functions just the same as any Mathematica function where the last statement that you return gets returned as the end result. In addition to these things, we've supplied you with these button form here, which allows you to clarify what your function looks like on the previous page. So where all you saw those blue blobs before that had a lot of information as opposed to a camel case, no spaces function name, you can actually figure out what your functions do just by reading the caption you've given them. And then additionally, for some further form of clarity, we have the template field here. And this template field will get imported into the input space when you choose your functions from the Your Functions header. And it allows you to customize the text between your function name describing what your function is doing, and then as well as some text between each of these variable fields. So that if you, say, have a quadratic formula equation, which I have back here, get into edit. So if you have this equation for a quadratic formula, I have my typical developer camel case function name that we use internally to reference this function, as well as the 3 parameters of a quadratic formula if you're a high school student and you're used to standard form, A, B, and C. I also have down here at the bottom the button form, just describing my typical camel case. We don't need much more clarity. But then here I have the quadratic formula for A equals B equals C equals. So when we look at this inside of the input field, then it will come out to look like this. And so it's actually descriptive of what your function's doing as opposed to just having a function with a bunch of arguments that you can't even read. So we can input values into here, say, I don't know, actually we'll do a really easy one. Let's just do 1, -2, and 1. So it's a really simple parabola. This is a function I created myself, and it gives us the end result roots for this quadratic equation. It's great if you're a high school student and you're trying to understand mathematics or implement something yourself. You can utilize this form to create a multitude of different equations. And then additionally, reference your own functions from other functions that you create. So one of the examples here is I have these find function roots and find function max min. They all have the general same formula where I'm solving for this equation just using general Mathematica code. It's a simple one-liner. We don't have to use TI-82 basic to create a lengthy program to do one thing. And then additionally, I have these find inflection points and then the find max min of each of these functions. And I combine them all into this plot critical points where I utilize a lot of Mathematica's code like plot style, and epilogue to draw a meaningful graph. And so if we actually look at this, and we'll plot it with the function, I've used labels here, with the variable x, and we compute this. Oh, I guess I'll show you the polynomial too, just so you can see it. So this is the polynomial that I've graphed here. This may, it actually kind of comes out all right, but you can see I've graphed the critical points of this polynomial. Here are the roots here, and the inflection points and the local maxima and minima of this polynomial. And it was all one line of code, just combining a lot of previous functions that I had written before. So as you build up an arsenal of functions, you'll begin to have a lot of capability. And some other examples I have, the unit circle, one of my favorite trigonometric properties, is it's the fundament of trigonometry in general. And so here we can describe to it some angle, which is indicated by my beautiful template here. And we'll get, some actual real information about the trigonometric properties of the circle. Instead of just calculating the sine or the cosine, we can actually visualize how these properties change. So instead of just looking at sinusoidal graphs and mapping graphs onto other graphs, we can derive meaningful information from these things and make useful visualizations. Magic. And so I have another example here too, or rather I'll do another example of the unit circle just so you can see what's actually happening. So we can actually see here now that the tangent line is going off to infinity, which is what we would expect as you get closer to 89 degrees. And cotangent and the cosecant become very, very small. And we can actually visualize what's actually happening as opposed to just looking at graphs of seemingly arbitrary numbers.
Do you add manipulation to that?
You cannot for version 1. But nonetheless, I have some other cool examples by our actually previously very own Teo Gray. This is one of my favorite Mathematica functions of all time. It's a beautiful one-liner that uses a lot of the functional programming paradigm, map indexes, nest lists, flatten, and things like that, to create a nice binary tree. And so this function looks really beautiful to me when you make it. So I'll start with a perfectly symmetrical tree. And so what I'm describing here with these 2 points are points about the origin where it's going to draw a single line, which I call the trunk, and we're going to describe 2 points off of that, which are 2 initial branches being bent. And then off of that, every branch will continue along this same angular formula. So if I enter a point here as well, and then I want 10 generations, and a line thickness degenerating from 0.8. We give it some time to figure it out here. All right, and we have our beautifully rendered tree. And what's nice about this is that I've drawn every part of it. So now instead of having to utilize calculator functions or built-in API, you have this beautiful visualization capability of the Wolfram language, instead of having to deal with nonsensical compiled language constructs on a small screen trying to do whatever. You can use this functional programming paradigm that the Wolfram language has to slowly build up more and more complex equations. And so I guess just as an example, too, of how complex these things can get, here's the code for the unit circle properties. And it is quite large, and there's a lot to it. But luckily, there's this big, beautiful code view that expands as you need to write more code. And so all of these things combined will give students or whomever else the ability to create meaningful representations of mathematics they're studying. So we can avoid just straight up computation of mathematics functions and move into understanding the math behind the math, if you will. And programming mode is quite potent. So I guess, do we have 5 minutes or do we keep going? All right. Well, thank you. I'll take questions if you guys want.